Thank you for staying here for the last session. I will be talking today about some of the work our group at NC State is doing related to UAVs. And I will then specifically talk about fusing elevation data from different sources, which we found useful in some of our applications in the context of water flow and erosion modeling. What's this? I'm sorry, it's not supposed to be black. Is this one? Okay.
Try this one.
Okay. I can just not have it full screen.
You can try the full screen as well. No, it's the same.
Okay, let's just keep it like that. Okay. So NC State has a partnership with Next Generation Air Transportation System, NGAT, and they are collecting the UAS data for us for different research and education purposes. And the data is then processed at Center for Geospatial Analytics by some of our colleagues. And the data is used for modeling by students and researchers. Okay. So we have been, as part of these efforts, we have been developing UAS Course. UAS means Unmanned Aerial Systems. It's also focused on LiDAR and other types of point clouds, basically. And this course covers most aspects of UAS, from flight planning, data collection, digital elevation model reconstruction, orthophotos, and then data analysis and modeling. Software is, of course, an important part of this course, so we expose students to both open source and proprietary solutions depending on the tasks. And students are working usually on their projects, which are of their interest, and they are usually quite interesting, like beaver dams and stuff like that. We also want them to learn some Python scripting, because that's very useful in this context too. This is our study area. So that's actually quite close to here. It's south of Raleigh, Mid-Pines area. And NGAT were collecting the data there since 2015. So we have quite a bit of data sets now, as you can see from the animation. This area, why they fly there is because it's part of NC State's property. It's agriculture field. And they mostly grow crops like corn and similar. So you can see kind of how dynamic the area actually is. So this data set, although it's not that interesting, but it still was giving us a lot of opportunities for exploring the change detection, and how it is linked with the processes like erosion and crop growth. And since we get this ultra-high resolution, here we are talking about 1 feet or even better. So we have this microtopography, which we can explore and learn from it about the errors from the reconstruction and stuff like that. So at this microtopographic level, we try to model landscape processes such as water flow, erosion, and also landscape evolution, so that we can better recognize and prevent erosion. For modeling landscape processes, UAS data processed through structure from motion present both opportunities and challenges, as you probably know. So we have really, really dense point clouds. We can get up to hundreds points per square meter, which is really more than you actually want. And with UAS, it's really simple to repeat the data collection. So we can have multiple data sets per year or month. The problems are more in the extent. So we are limited by the batteries of the drones, of course, but also some areas you can't even fly because there are houses. So that's the limitation. And then big limitation is actually we don't get the ground data, depending on the type of vegetation. But for example, here it's a dense corn, and you don't get any ground points there, which poses a lot of challenges for modeling. As you can see, you get really weird water flow patterns in there. So you are basically overestimating at one point and then underestimating downstream. On the other hand, we have in the state of North Carolina, we have really great LiDAR data, and they are pretty dense, and they will be even better with the new LiDAR sensors. So we have currently 2 or 3 points per meter squared. The problem is a LiDAR is very expensive, and you can't, in terms of flying, and you can't really repeat it very often. But on the other hand, you get a large area, and you get the ground data. So since both UAS and LiDAR-based digital elevation models have their advantages, we will often have to combine these data sources. So that's what I wanted to talk a little bit about the digital elevation model fusion, or you can also call it mosaicing, patching, merging. However, I use fusion mainly because it sounds cooler. So the motivation here is kind of what I was already saying when I compared the LiDAR and UAS data. So the boundaries of the UAS-based DEM and the modeled water flow or phenomenon don't match, for example, with watersheds, because the whole watershed is not captured in our US-based data set. Then in our UAS data, we don't get ground, but we have the ground in our LiDAR. And then we have the older LiDAR data or older US-based DEM, but we need to update some specific part with the newest data. So these are all the kind of requirements or needs you have. So what we were looking for our use cases specifically was a simple but robust GIS-based method, which would be raster-based, because that's because our models are based on rasters. And because we are focused on modeling of water flow, we wanted to actually have the transition between the models very smooth. So this is the type of problem you get if you approach it in a very naive way. So when you just patch 2 rasters with the raster algebra expression, so you can see you get a visible boundary even when the surfaces actually match quite well. You can get even into worse situations, but you can still see the boundary. And it might not matter for your application, but if you are trying to model water flow, you get really kind of weird patterns. So in this case, we are actually we're trying to patch 2 UAS-based digital elevation models, where in this part we had high crops. So we cut it out and put their UAS base DM from a different time. But you can see you get a lot of kind of bonding here and along this line, which is not naturally occurring. So what we basically need is a very smooth transition. So this is how we want it to look like. So you can see no more weird bonding. And it still captures the gully, which is in here. So we developed, we started with this fusion method, version 1, which is a simpler. So I will explain it quickly. And then we built on top of it and created a little bit more complicated version with better properties. So here, let's say we have a digital elevation model A, which is usually our UAS-based DEM, which means high resolution or more detailed. And then we have B, which can be LiDAR or stuff like that. And so we will be basically computing weighted average of the DEMs on their overlap. And the overlap zone has width S. I will use it in further equations. So what we basically want is this. So this is the LiDAR, let's say, this is the UAS, and we want to smoothly transition from one DM to the other one. So we need two DMs which have the same resolution. So you have to adjust their resolutions before you actually get to this fusion step. And then the only thing you need is actually raster algebra and some kind of Euclidean distance tool. So step 1 is you compute the distance from edge of dataset A inwards, and that's, for example, in GraphJS, it's this command. And then, so equation, but don't be worried, it's really easy. Then this is basically a linear combination, or you can also say it's weighted average of the surfaces based on the distance from edge of the dataset A. So here, this is this is all what you need. So it's distance from the distance we computed in the first step. And this is just a raster algebra expression. So this is how it will look like based on the smoothing parameter S, which is the width of the overlap zone. So this is without smoothing. You can see the edge there. And here there's more smoothing up to here, where here you get a lot of smoothing, but you can't really recognize where one data set ends and the other begins. So this approach, as you can see from here, has the limitation that the overlap zone is has a single width. So the problem here is that here this part has actually much higher difference between those two data sets than the part here. So, but if you have only a single width, then everything is going to be smooth in the same way. So we were thinking that there's no reason to do that, that we should instead use a overlap width, which is basically driven by the data, by the differences between the data sets on the edge. So the advantages of that is that we get more gradual transition where the differences between the data sets are high, and at the same time you preserve the subtle features of both DMs where the differences are low. So this picture here should explain that better. So here again we are fusing, I think, two US-based digital elevation models. So for example, here on the edge, there is really small difference. And this translates into really small width of the overlap zone. Here, there is a bigger difference between those data sets, and this results in bigger or wider overlap here. How you can actually implement that? So it's a couple steps. It's not really that difficult. Basically, you start with the same step as in the previous method. So you compute the distance from the edge of the data set, compute absolute difference between the data sets A and B, and you extract a 1 pixel wide edge as raster. Then, based on this edge, you create a raster where each cell has the value of the nearest cell from that edge. You combine the raster from step 1, the distance, and the raster with the differences from step 3, and create a raster representing weights. And then again, you compute the linear combination of the DEMs as in previous step. Okay. So, and finally, I just wanted to show you a kind of fun use case of this method. Tangible landscape, you might have seen it in our NC State booth. So basically, it's a tangible interface for GIS. It couples malleable physical model with digital landscape through the cycle of real-time scanning, analysis, and projection. So whatever you change here is going to the scanner, to GRASS GIS, where you compute the stuff and project it back. And so here, for this application, we were using it for developing and testing methods for controlling storm water flow for our field in Mid-Pines, where we have these developing gullies. And so we needed the smooth fusion of the data set created by the Kinect, which is limited by the model. And we wanted to fuse it with the larger LiDAR data set, because basically this model doesn't cover the whole watershed. So we need the water to flow basically into the model, where we do some intervention, and then it will flow out of the model. The model itself is georeferenced, and it has the shape of the actual landscape in that part of our study area. So, and this is basically the result. So you can see here, this is the model, if you can see, and we project the whole orthophoto and the water flow simulation on the table. So the table is around here. And so you can see it with the smooth fusion, it actually goes smoothly out of the model and flows into the model. So once we have this, we modify the landscape. So this is where the gully develops. Here you can actually create some checkpoints or to experiment with erosion. And again, the smooth fusion is used here in this model. So just finally, so this method, it's pretty simple. You can implement it actually yourself in your favorite GIS, because it doesn't use any specific tools. But if you want, there is the implementation in GRASS GIS r.patch.smooth, which is on GitHub, and you can install it in GRASS. And we also provide some data set for testing. And this is the GUI if you are scared of command line. Yeah. So thank you. That's all from me.
Any questions for
Mhm.
Is part of your process adjusting the data so that you get a nice, smooth,
Yeah.
kind of part of your process?
Um, So it's not part of this. This assumes already that you were able to match it as best as possible. We didn't really have this problem because the LiDAR data are really in a good shape, and the UAS data sets, we had GCPs which pretty much improved the UAS-based data sets a lot. But we were trying to, in some cases, the UAS datasets where they had some kind of weird distortions. So we were actually trying to, or I was basically extracting like a smooth distortion surface, and then I applied to that data set. And I think you can do that only depending on your application, because we are really looking at the microtopography. And if you change the shape of the DEM to match the LiDAR in a very small or subtle way, it won't really impact your water flow while you are still keeping the microtopography on the surface. But for this method, it's just it expects you to already fix your data